Okay, so we're going to take a look at geometric series, which is section 1.4 in your textbook. And so a geometric series is the expression for the sum of the terms of a geometric sequence. Okay, so just to recall, a sequence would be your list of terms. Okay, so for example, you could have 3, 9, 27, and so on. A series then is the sum of the terms. So in this example, it would be 3 plus 9 plus 27 plus, and so on. So let's take a look at an example of what that would look like. A school district emergency fan-out system is designed to enable important information to reach the entire staff of the district very quickly. At the first level, the superintendent calls 2 assistant superintendents. The 2 assistant superintendents each call 2 area superintendents. They, in turn, each call 2 principals. The pattern continues with each person calling 2 other people. At every level, the total number of people contacted is twice the number of people contacted in the previous level. The pattern can be modeled by a geometric series where the first term is 1 and the common ratio is 2. The series for the fan-out system would be 1 plus 2 plus 4 plus 8, which gives a sum of 15 people contacted after 4 levels. To extend this series to 15 or 20 or 100 levels, you need to determine a way to calculate the sum of the series other than just adding the terms. And that is because it becomes quite laborious, right, to work out what the sum of 100 levels would be. Okay, so let's take a look at this diagram and get a picture of what this series looks like. You have your superintendent at the first level, so that's one person, and this is level 1. He calls 2 assistant superintendents. Okay, so we've got 2 people called at level 2. These assistant superintendents call 2 area superintendents each. Okay, so now we've got 4 people who are contacted at level 3. And then each of the area superintendents calls up a principal. And so you can see at this last level here, we have 8 people who are contacted. Okay, so at level 4, 8 people. So the series then is 1 plus 2 plus 4 plus 8, which gives us a total of 15 people who are contacted at the 4th level. Okay, well, it does get to be quite a bit of work if we have to work out, more than 5 or 6 levels, let's say. So we can use formulas. Now we have 2 formulas here. Okay, we'll just take a look at the first one up here to start with. The sum of a geometric series can be determined using the formula S subscript n equals T1 times 1 minus r to the nth power all over 1 minus r, or just rearranging the 1 and the r to the n and the 1 and the r in the denominator, you would get T1 times r to the n minus 1 over r minus 1. They really are the same formula. And something to keep in mind, in both cases, r can't be 1. And why is that? Well, because the denominator would become 0. If I plug 1 into here, okay, then I would get 1 minus 1. If I plug 1 into here, I would get 1 minus 1. So here, just as a note of explanation, if we have a denominator of r minus 1 and we plug 1 in for r, we would get 1 minus 1, which is 0. Okay? And as you remember from your past math courses, you cannot divide by 0. Okay, another thing to keep in mind, with regards to a geometric sequence or series, r cannot equal 0. Why is that? Well, let's take a look. Our first term we're going to call T1. If I want to build up a sequence, a geometric sequence, then I would have to take my first term and times it by my common ratio. And if my common ratio is 0, then to get my second term, I would take my first term and times it by my common ratio, which is 0, and 0 times anything is 0. So you can see your term 2 would be 0. That was also true for term 3. To build term 3, you would take your first term and times it by your common ratio twice, so t1 times 0 times 0. You still get 0. And so you're not getting a geometric sequence. All you're getting is t1 and then 0 and 0, and the next number is going to be 0. And so r cannot equal 0. Okay, we have a second formula that we can use to calculate a sum. It's s subscript n equals r times t subscript n minus t subscript 1, all divided by r minus 1. Now, you would use either one of these two formulas depending on the information that you have. So for the first one, it's ideal for you to use this one when you know what the first term is, t subscript 1, what the ratio is, r, and what the number of terms is, n. Okay? And on the second one, it would be ideal to use this formula when you know what the first term is, when you know what the common ratio is, and when you know what the last term, t subscript n, is. Okay? All right, so that concludes our introduction. Okay, so example number 1, determine the sum of a geometric series. So I have our formulas written at the top so that they're easy reference. And let's take a look at our first question under example 1. Determine the sum of the first 12 terms, S12, of this geometric series. You have 3 plus 12 plus 48 plus 192, and so on. Okay, so let's start by writing down what we know. We know that T1 is 3. We can calculate R by going T2 divided by T1, so that's 12 over 3. That gives you 4. And of course, you know that you can work out your common ratio by going 48 divided by 12 or 192 divided by 48. Both of those should give you 4. And the other piece of information that we know from the problem is because we're looking for S12, we know that n, our term number, is 12. So looking at our formulas, you can see that we're going to use the first formula because we know what T1 is, we know what R is, and we know what n is. So we're looking for S12, and in place of T1 we're going to put 3, in place of R 4, in place of n 12, and in the denominator r minus 1, so 4 minus 1. Okay, so using order of operations, we're going to calculate first what's inside the bracket. Remember, you first need to work with your exponents. So you're first going to figure out what 4 to the 12th is, and then minus 1, and you should get 1, 6, 7, 7, 7, 2, 1, 5, a rather large number. And in your denominator, you will get 4 minus 1, which is 3. Okay, notice that you can reduce your 3's, which leaves you with the answer of 167, 77, 215. Okay, 16,777,215. Big number. Okay, on our next example, you've been asked to determine the sum of the first 15 terms of this geometric series and to write your sum to the nearest hundredth. So your series is 4 minus 20 plus 10 minus 5 plus 2.5. Okay, we want the first 15 terms, so we're looking for S15. What do we know? We know that T1 is equal to 40. We know that R is T2 divided by T1, so negative 20 over 40, which is negative 0.5. And because we want to know the sum of the first 15 terms, we know that n is equal to 15. So once again, we're going to use our first formula because we know what T1 is, we know what R is, and we know what n is. So S15 is equal to T1, which is 40, times R to the n power, and I need to put this in a bracket, okay, to the 15th, all right, and then minus 1 over 1 minus, sorry, R, which is negative 0.5 minus 1. Okay, so why do we put negative 0.5 in a bracket? Okay, well, because our base is negative, we need to put it in a bracket and raise it to the power to show that we are not only going to raise the 0.5 to the 15th power, but also the negative. Okay, and it makes a difference, especially when your exponent is an even number. Okay, so just over here, let's take a look at some information that you should know from your past math courses. If you have negative 4, let's say, to the second power, this means negative 4 times negative 4, which is 16. If you have negative 4 to the second power, okay, and all you're squaring is your 4 because that's what your base is, then the question becomes negative 4 times 4, which is negative 16. Now, we can take this and raise it to the third power, okay, and this would mean negative 4 times negative 4 times negative 4, which is negative 64, okay, and compare that to negative 4 to the third power, where we go negative 4 times negative 4 times negative 4, and that would give you negative 64 also. Okay, so notice in terms of calculating, if your exponent is an odd number and your base is a negative, it's not going to matter really whether you put the base in a bracket or not, because your answer will still be calculated correctly at negative 64 in this case. But if you have a negative base and your exponent is even, it's going to matter that you have your base in a bracket or not, because if you have a negative base and you're squaring it, okay, to an even power, you get a positive number for your answer. If you don't put your negative number in a bracket, then your base is 4, not negative 4 now, and your answer turns out to be negative 16. So it really does matter whether you use brackets or not when you're dealing with a base that is negative. Okay, so getting back to our question then, we're first going to calculate what's inside the bracket. Okay, so we're going to go 40 times, and you're first going to calculate negative 0.5 to the 15th power, and then minus 1 from it, and you are going to get negative 1.000030518, and divide that by negative 0.5 minus 1, which is negative 1.5. And then finishing off the calculation, you're going to go 40 times negative 1.000030518 divided by negative 1.5, and you should get an answer to the nearest hundredth of 26.67. Okay, so that finishes up our first example. Okay, so we're going to take a look at two more questions. For example number 2, where we determine the sum of geometric series. I have our formulas at the top here again for easy reference. And on the first question, you've been asked to determine the sum of the 10th term. So S subscript 10 if T subscript n equals 5 times 2 to the n minus 1. So notice you are given the general term. And from the general term, you are going to find the information that you need in order to find a sum. Okay. So from our general term, what do we know? Okay, well, because the general term is T subscript n equals T1 times r to the n minus 1, you can see that your first term is 5. And you can see that your common ratio is 2. And using the general term, we can't tell what the value for n is, but because we are asked to find the sum of the first 10 terms, we can see that our n term is 10. Okay, so going to our formulas, it looks like we're going to be using the first formula again, right? Because we know what T1 is, we know what r is, and we know what n is. So S subscript 10 is equal to the first term times r to the n, so 2 to the 10 minus 1. Divide it by r minus 1, which is 2 minus 1. Okay, first determine what's inside the bracket. So 2 to the 10 minus 1 gives you, let me work that out because I haven't done that yet. So 2 to the 10 minus 1 gives you 1023. And divide that by 2 minus 1, which is 1. Okay, so you're going to go 5 times 1023. And you should get 5115. Okay, so the sum of the first 10 terms is 5,115. Okay, so for our second example, we've been asked to calculate the sum of a geometric series 6 plus 12 plus 24 plus 48 plus ... plus 12,288. So what we know is that T1 is 6. We can calculate R by going T2 over T1, which is 12 over 6, which is 2. And remember, you can go 24 divided by 12 or 48 divided by 24. You should still get 2. And we're given the last number in our geometric series, so we know that T subscript n is 12,288. So we're going to use our second formula, okay? Because we know what T1 is, we know what R is, and we know what T subscript n is. So we don't know what term number 12,288 is, so we're just looking for S subscript n, but we can plug in our R value, which is 2, times our T subscript n, which is 12,288, and minus T1 from that, and then divide that by R minus 1, so 2 minus 1, and you can see that the sum for this series is, first simplify what's in the numerator, go 2 times 12,288 minus 6 from that. That gives you 24570 divided by 2 minus 1, which is 1. And so our sum for this series is 24,570. So that's the end of example 2. Okay, so application problems, example number 3. We're going to take a look at 2 questions. One that deals with a lottery scenario and one that deals with an oil production scenario. Okay, so in the first one, in a lottery, the first ticket drawn wins a prize of $25. Each ticket after that receives a prize that is twice the value of the preceding prize. You're asked to write a function to model the total amount of prize money given away. So total amount is going to suggest a sum. So let's write the series for this. We start with the first prize of $25, and then each ticket after that will receive a prize that is twice that value. So twice 25 is 50. Twice 50 is 100. And so we can keep building it by multiplying by 2. Now we do want to write a function, so we're going to start by using our sum formula, and it's r to the n minus 1 over r minus 1. Okay, and write down what we know. We know that T1 is 25, and we know from the problem that r is 2. Now if you haven't figured that out from the problem, you can work it out by going T2 divided by T1, so 50 over 25 is 2. Okay, so let's plug these numbers into our formula. So we go 25 times 2 to the n minus 1 over 2 minus 1, and simplify. And we get 25 times 2 to the n minus 1. Okay, and there's nothing in the denominator except 1, because 2 minus 1 is 1, and we don't need to write that in the denominator. Now, you've been asked to write a function. So I'm going to let P be the total amount of prize money given away. Okay? And now I can write my equation or my formula here as a function. So I'm going to say P of n, okay, because my variable that I'm using is n, is equal to 25 times 2 to the n minus 1. And now you have a function that will model the total amount of prize money given away. Okay, so on the second part of the question, you've been asked to determine how many prizes are given out if the total amount of prize money is approximately $2 million. Now, we know from our function that P of n is the prize total, prize money given, away, and that must mean that n is the number of prizes. Okay? All right, so let's substitute in 2 million for P of n. And that's equal to 25 times 2 to the n minus 1. So you can see from what we have written here now that n is our variable, and we need to isolate our n. Okay, so we're going to start by dividing both sides by 25. And so 2 million divided by 25 is 80,000. And that's equal now to 2 to the n minus 1. Okay, and then we want to isolate the 2 to the n, so we want to bring the negative 1 over and it becomes positive. So we have now 80,001 is equal to 2 to the n. Okay, so your exponent is a variable. All right, and how do we solve for variables that are exponents? We use logarithms. So just to remind you, the log of the argument over the log of the base is equal to the exponent. Okay, so we need to remember what our argument is and what our base is and what our exponent is. So the 80,001 is the argument. Your base is the 2. And the n is the exponent. Okay, so let's plug that into our expression here. So the log of 80,001 over the log of 2 is equal to our exponent, which is n. Okay, so plug into your calculator and you find that n is 16.2877, but we want to round that down to 16. Okay, we don't want to go over 16 because then the amount of prize money would be more than $2 million. Okay, so 16 prizes were handed out. Okay, so let's take a look at our second word problem. A well produced 10,000 barrels of oil this month. The well produces 20% less oil each month. Determine the number of barrels produced over 3 years. Okay, so they want to know the number of barrels produced over 3 years. So that means that we have a sum question here, okay, which means that we need to write a series, okay? So we're going to start with our 10,000 barrels. And we know that in the next month, the production is 20% less. So we need to figure out what 20% less of 10,000 is. So we're going to go 10,000 times 0.2. That gives us 2,000. And then we minus the 2,000 from the 10,000 and we get 8,000. So there are 8,000 barrels in the second month produced. And let's just work one more out. So let's figure out what the third month is. So that's 8,000 times 0.2, which gives us 1,600. And 8,000 minus 1,600 is 6,400. And so our third term in our series is 6,400. Okay, so let's write down what we know. We know that T1 is 10,000. We know that R is T2, 8,000 over T1, 10,000. That will give us 0.8. And we also know N, which in this case is going to represent the number of months because our oil production is per month. We have 3 years, so 3 times 12 months. And so the period of time that we're looking at is 36 months. Okay, so I'm going to use the second form of the formula for sum that we were given, just to show you how to work that one out. So let's plug in our values for N, R, and T1. So we're looking for the sum of 36 terms. That's equal to 10,000 times 1 minus our common ratio to the power of 36 over 1 minus 0.8. Okay, so S subscript 36 is equal to 10,000 times, and then we're going to go 1 minus 0.8 raised to the 36th power, and we get 0.999675 over 1 minus 0.8, which is 0.2. So we put all of this into our calculator, and we get 49984. Okay, so 49,984 barrels were produced over 3 years. And so that concludes our our section on geometric series 1.4.